Our guest speaker today is John Nairn, and I was fortunate enough to see John speak at a state government event late last year, hence the invitation to speak to us today. Just a little bit of background on John. Since joining the Bureau in 1980, he's pursued client-focused deployments in Antarctic operations, severe weather events in Melbourne, specialist airport operations in Sydney, Sydney Olympic and Paralympic Games, and multiple interstate bushfire emergencies apart from his normal forecasting roles in Victoria, South Australia and New South Wales. John has been the Regional Director since 2014, following an extended period as Weather Services Manager in South Australia. John has developed the Bureau's Heatwave service and visited the UK, Germany and USA in 2013 under a Churchill Fellowship to study heatwaves. He has an MBA, a DipEd, a Bachelor of Science Honours in Meteorology and Oceanography, and is undertaking a part-time PhD on heatwaves. Would you please welcome John Nairn, the Regional Director, SA and National Heatwave Project Director.
Thanks very much. It's quite a pleasure to be able to come here and talk to such an august group. I don't know if I'll get to meet you all, but it's really nice to be able to be here today. As you'd imagine, I could tell you a lot of stories. You know, there's a lot of things I've done. I could talk to you about heat waves, and in fact we're going into a heat wave right now, and I do urge you to make sure that you hydrate yourselves well over the coming days. So it's really important. Just make sure I've got this right. But what I thought I'd do today is talk to you about the recent heat wave that we had on the Great Barrier Reef and how that plays into our consciousness around the way that the globe is responding to the changes that we see. So if I get this right, here we go. So the Great Barrier Reef heat wave, it pretty much bleached very thoroughly about the top 50% of the reef. The gradation in depletion of the reef fell off rapidly as if it went south, and I know some politicians went swimming on the reef with great aplomb to demonstrate that the reef was in great health, but they did visit the part that wasn't hit by the heat wave. And this is a continuing feature of my work, but never mind. Ocean temperatures, global warming is actually quite evident in the temperature record for the Great Barrier Reef. And you can see here since 1900 that the temperatures, and these are very reliable records, show that we've been through a transition here in terms of warming. And look, today the reason why I've concentrated on an ocean body rather than the atmosphere that we breathe is that the conversation around global warming is rather heavily debated around atmospheric temperatures. But when you understand that the specific heat that it takes, you know, the energy it takes to heat the atmosphere is a fraction of what it takes to heat the oceans, the debate should actually be conducted on the oceans because the evidence there is overwhelming. So I just think it's because we live in the atmosphere that we're having the debate about what we live in. It's just a bit of an odd thing. But anyway, look, I wanted to talk about how the El Nino was part of what drove this marine heat wave. And if you look here, you'll see Australia, South America, and classically in the El Nino, we see a warming in the mid-Pacific. We end up with a heat anomaly, as we call it. And as a consequence, you see a lot of, over a warm ocean body, you'll get a lot of rising air. And that warm ocean will release a lot of water vapour, and so therefore you'll get a lot of cloud precipitation in this rising column. But wherever we get rising columns of air, we must have a compensating descending air column. And what happens is, in an El Nino, we have an anomalously cool patch to the north of Australia. So yes, our tropics are generally warm oceans, and it's not like they become cold oceans, it's just that they become cooler than normal. So, 28 to 26 degrees or something like that might drop a degree or two. and out here in the Pacific, the Central Pacific, it goes up a degree or two. And on a global scale, that makes a difference to the way that our winds move. So the net effect is that we end up with a wind that tracks away from us. And as a consequence, this feature is actually well understood, the El Nino, for driving drought, particularly in our eastern states. And what happens is these westerly anomalies pull the interior winds across these productive areas of the eastern coasts, and they end up in a long-term drought. So that's the El Nino cycle. And you'd appreciate that 2016 was the maturing of the El Nino, and we had this process endemic at that time. And what also happens is, because these storms are not over Australia, but in fact we've got this descending motion in this area, there's a lack of storms. So intermittent activities of winds rushing through and with storm activity means that the lagoons of the Great Barrier Reef, which is a trapped body of water really, doesn't get to overturn. So the waters become very, if you like, stagnant, but in terms, they become rather stratified. So rather than being a mixed body of water, you end up with a very shallow, very hot layer and sitting on top of what might be considered to be normal temperatures below. So unless you stir those waters, they get very hot in the top layers. And of course, that's where the reefs lie. So the world's oceans, I suppose we should just consider what they are. 71% of the Earth's surface, the average depth of nearly 4 kilometres, a very large number in terms of the volume in cubic kilometres, 840 times the density of air. So you'd appreciate that when you put on the hairdryer, it's not hard to make that air hot. You put the same energy into water and you won't notice a change in temperature. Because of that density, it takes a lot more to the specific heat of water, it takes a lot more energy to actually warm it. So from space, compared to the landmass, water is a dark body. And what does that mean? What it means is it absorbs more energy from the sun. So it doesn't release as much energy as the landmass. The landmass will actually reflect, it's called the albedo, will reflect much more energy, but also some of the radiation that goes in will actually be absorbed and not re-released. Not readily anyway. And it embodies more than 90% of global warming in terms of what we've seen. So the heat content of the oceans is actually really well measured. No one ever debates it because no one comes up with a contrary argument. Now you understand I've made a very significant statement there in terms of global warming. No one debates the warming in the oceans. It's 90% of the global warming. I don't know why we have a debate. Anyway. Oops, sorry. Oh, damn it. I think I've gone the wrong way. So anyway, so most of the heat that we've gained from the greenhouse effect is going into the oceans. There's 93% of that in total. 2/3 of that is in the upper 700 metres of the ocean. So that's in the area where we interact with the ocean most. 30% of it is below that level. Really interesting, that 30%, because we have in the science literature you'll see people debating interdecadal cycles in terms of our climate weather. This energy that's being pushed deeper into the oceans revisits us on decadal cycles as we overturn the oceans. So we're yet to see some of this energy come back to us, and it's actually a very interesting feature of how we look to our future climates. So the ocean content has increased by around about a very large number, 30 by 10 to the 22 power of 22 joules since 1970, and it's just staggering. So these are our global ocean surface currents. You'll have to believe me when I talk about there's lots of eddies in here and little squiggles, but basically you can see that in terms of there is different circulations, quite a lot of different circulations around the oceans that we monitor quite well. And I will say that there's been a revolution in the observing of the oceans since the satellites have been introduced, and also in terms of instrumentation such as the Argo floats. Can I have a show of hands for those that have ever heard of the Argo floats? So I'll spend a moment on that. The Argo floats are actually very interesting. There's thousands of them out there, and they've advanced our science in the oceans enormously. Very cute thing. They're about that big, and they have a little bladder in them. And what they do is they sit out in the ocean, they float, but when they're ready to, and they communicate by satellite their messages from the instrument. And they're gathering data all the time on air pressure, or pressure from the instrument, temperature, and I forget which. They may be the two primary measurements. But there may be a salinity measurement, I can't remember. But it deflates the bladder and it descends to about 1,500 metres. And it sits there and goes along in the very slow ocean currents. And it's a way of actually staying stationary rather than being moved around on the ocean surface too much. And then it reinflates the bladder, comes back to the surface. It's got all this data, the temperature profile that's gone through the ocean. It's collecting data on what the structure of the ocean is, and it comes back up, and then it transmits that by satellite. We have these soundings of the ocean that have been going on now for some 15, 20 years that are covering the oceans, and it's a fabulous data source that's actually advanced our science. Of course, there's lots of satellite data as well. So this is the summer sea surface temperatures in the Great Barrier Reef. So looking at summers only, we're seeing how, if you like, if you concentrate only on the red, the incidence of summer extremes has changed. So back in the 1920, there was an event back here in the 40s, and there were some decent heat waves in the 40s. A couple of events in the 50s, in the 60s, there's a bit. During the 60s and 70s, we had a very wet phase in our climate, and it was a bit cooler. It's a well-known wet phase. And then we've seen a steady rise in the incidence of extremes. So there has been a rather dramatic increase in the intensity and frequency of summertime temperature extremes in the Great Barrier Reef. So there are different ENSO, El Nino, Southern Ocean patterns. Acronyms live in every industry, I'm sure, but that's what ENSO stands for. The El Nino I explained before. The neutral pattern, which is what we would look for being just the normal pattern, so it's normally cooler near Chile from upwelling, which feeds the country of Chile with their pilchard and anchovy harvests, because the nutrients rise in the ocean, the sun hits it and all the biota takes off, and that's a normal state of affair for them. They make their industry out of living off of that. And normally we're warm to the north, so we just get this trade wind, this Walker circulation as we've called it. And then you get the La Nina phase, where we become anomalously warm to the north, the famous 2010, 11, 12, where we actually had enormous rains over Australia. And this is anomalously cool, and it drives the wind toward Australia across those warmer waters into us to produce heavy rains. Below it is the structure of the oceans, how that thermocline there changes in this circulation. So there's an overturning of the ocean, if you will, in terms of the way that structure is set up in the top several hundred metres of the ocean. So some effects of the El Nino in 2016 is seen in these sea surface temperatures in the Great Barrier Reef, and you'll see here, this is actually an image of outgoing long-wave radiation, OLR. That's the radiation that we emit back out to space from the oceans, the land masses. They absorb the radiation, and then they radiate at a natural wavelength for that, and that's the cooling process that we normally get in the oceans. What it's showing here is that lower radiation goes out means there's a lot of cloud in there. There's a lot of cloud in here, and where it's warmer, where it's very large amounts of radiation going out, sorry about that, oh, I've just pressed the wrong button again, we get no cloud effectively over this area. A lot of radiation gets in and it heats the surface. So that's part of what's going on because we've got this down motion in the atmosphere that's keeping the skies clear. And that's effectively what that chart is telling you is going on. So weak winds reduce the lagoon overturning, and the East Australia current, which is an intermittent current in its own right, is keeping the waters warm near the coast even as far as Tasmania. So it's transporting that energy, that warmer waters down. So the bleaching event in 16. You'll see here, this is the February sea surface temperatures for the Great Barrier Reef, and that in these events in here we're seeing temperatures that we've never seen before, that this reef that we know has not experienced. So these are the temperatures that the coral doesn't function very well. And indeed, as we go on, we find that by March, February, March, a month later, this exceedance continues and it's not been seen before. So that's the reason why it was actually such a large event. The heat wave, the ocean heat wave, if you will, it was nasty, yes, it's similar to ones we've seen before, but it extended a month longer. So it actually went on to expose the reef to a much longer period of heat. So the peak of the Great Barrier Reef heat wave, so February was the hottest summer month on the Great Barrier Reef. We had sea surface temperatures up to 31 degrees Celsius. Some areas in the north of the Great Barrier Reef were 2 degrees Celsius above average. And it's not like it's a weather event where you can get a southerly change through and you get a relief and then you go back into a heat wave. In the oceans, these features occur slowly and steadily with a lot of momentum. There's nothing that will get in there to provide a temporary relief. It actually just keeps on coming. It's more like a tsunami of heat, if you like, in the ocean. So what we ended up with is, in terms of our oceans, if we've monitored them, is our hottest ever sea surface temperature record. So on the right here, this is a calibration, if you like, on whether the temperature is average in the white, whether it's above average, very much above average, or highest on record. And so in this particular event, we had this rather large area out here, highest on record. This has contributed to the wet winter we've had. I could talk about that, but effectively the wet winter we've had is an Indian Ocean phenomena where the tropical waters near Australia are hot on average, and out to Madagascar way, northern, it's cooler. And like the other circulations I've shown you, it drives the winds towards Australia, picks up the moisture, and we capture it in our systems and get lots of rain. And I'm sure you'll all agree we've had a lot of rain. Yes. So here we see that we've pretty much had highest on record, and you can see how this water has been drawn down the coast in here. Now, whilst these temperatures here aren't the same temperatures as those seen here, all around Bass Strait and around Tasmania, these were the highest on record in terms of the temperatures experienced in that area. And hence, as I'm sure we've heard, we've seen the retreat of the kelp forests and other things like that. They're being impacted by temperatures that they can't survive in, and they're disappearing. So what I'm showing you here now is showing you the cumulative temperature degree days that we're experiencing through this period. And you can see that in terms of the advice that we had from the reef people, green was okay through December. Yellow was, you'd have to watch out for that sort of temperature as to whether it's going to have impact. And orange was a definite worry. And so this is just recycling again through those temperatures. And you can see it starts in December, but it goes through to March. So it's actually going through December, January, February, March through this cyclic chart. And I'll let it run one more time before I move on. But you can see in there that there is no relief. It just keeps on accumulating as you go on. And yeah, probably you can read that for yourself. So this talk was actually constructed in March. So the question then was, what's the future? You know, what were our numerical modelling guiding us on what was the future outlooks for the reef? And as we look forward in terms of anomalies for the time of year, There's a fortnight one, the first fortnight out from start date of, well, that's the 21st of April, starting from 21st of April. So there's a warm anomaly in the coast there on the reef. If it's red, it's warmer, the redder it gets. If it's blue, and there's a little bit around Papua New Guinea there, it's a little bit cooler than average. And what you see through here is a fortnight out, the next fortnight out, the month out, the second month out, into June 2016, the warm anomaly continued, so it was a rather persistent feature. Then we go July, August, September, October. By this stage, it's breaking down. It's a very long time to be in warm anomalies. So, I've added this in so you could get an understanding. So I'm finished on the Great Barrier Reef story, but this is now your winter, what you've been through. And I'm showing you here the July, and I've forgotten the East Coast because I'm more interested in where I live now. Oh, sorry, oh, damn it. Nearly there. I know I don't have much time. But this was the warm anomaly that has fed us the moisture into Australia that's given us the rains. The temperature of the oceans are warmer than they should be. When they're warmer, they will give us more moisture in the winds that pass over them that come to Australia. So we load up the atmosphere. The other thing is, at this point in time, the literature shows that we've reached 1 degree warmer globally than average. For every degree warming under that measure, the atmosphere can hold 7% more moisture. So as we push this moisture towards us, we're seeing an atmosphere laden with more moisture than we've seen before, out of record temperatures across these oceans. I will say that in the last rainfall events, we've been ticking away the records consistently. The atmosphere, when we measure it with our balloon soundings and the like, and our models, we look at the column of air and we say, how much precipitable water is in there? We're cracking all-time records when we see 60 millimetres of precipitable water. Now, if you sit the atmosphere and keep on feeding it over you, you can get 100, 200 millimetres if you keep on pushing that same atmosphere over you, right? So, where did that precipitable water come from? It came from this body of ocean out here. And what happened was what we called a negative Indian Ocean dipole. This is the cooler air. So there's a descending column of air over this and ascending, rising air over here, and that drives a direct recirculation that pushes the atmosphere toward us and lifts the air over Australia, and it gets caught up with the atmospheric systems that then deliver it as rain over us. So that's what back in July we had, and it was a very strong, about as strong as we have in our records for a negative Indian Ocean dipole. And as we move forward, and this is February the 6th, so this is showing you that that's breaking down. So you can see that the warm anomaly now is sitting more down here. There's much more closer to average temperatures. You'll see it, the blues are much lighter. They're still warmer, but they're lighter. Well, the blues are in fact cooler, which is what we're expecting to do. So there's still coolness out here, but there's a bit of coolness down here as well in terms of the anomaly. So, really speaking, we're expecting that going forward, the coming seasons, we are going to cease the heavy rainfalls that we've seen in the past. And last of all, just to go, because you will have heard about it in the news, these are the anomaly maps for the North Pole. And I just thought I'd mention that the enormous amounts of snow and everything else, the very cold event in Europe, is actually a feature of global warming. Now, shoot me. But the problem is, because the pole is so warmer than it used to be, the jet stream around the North Pole has weakened. And as a consequence, it's meandering more. And a meandering jet stream will park a weather system in one spot. So you're hearing about the cold blizzards, but you're not hearing about the warm anomaly in the other part, over the ocean or another country. And I talked to a friend who returned from Pakistan recently, and they had 6 months where they had no rain in a warm anomaly, where normally they'd have snow and cold winter. So there you go. Thank you.
Thanks very much, John. We might just kick off with some questions. I've got one I might just quickly ask first, though. I read recently that you talked about the North Pole and the northern part of the globe. I saw that temperatures in the North Pole were around about 20 degrees higher this year. Was that correct?
That's exactly what that shows. So, in the scale here, this is the difference from average temperature. That's 0, and that's 32 degrees Fahrenheit, 18 degrees C. So you'll see it's never uniform. The world is not an even sheet, and so therefore it's always easy to look at the discussion that you're interested in talking about. I'll go over here and talk about the weather, but when you look at this region across the pole, you see the very warm anomaly in here. So when the news story was running that they'd reached 20 degrees more than normal, it was that part of the globe they were talking about.
Right. Thanks very much, John. Adrian Sesternino, got a question?
I've got a question is to do with that chart where we saw Tasmania there, Tasmania being abnormally high in temperature,
Yes.
and then the northern part of Australia. Why the parts in between are not? What explains the fact that?
Yeah.
And in particular, I would have thought maybe because it's shallow water ocean around Tasmania, then it is farther away. But then even South Australia, the west coast of their peninsula is very shallow as well. But
Sure.
the same phenomenon.
Sure. So, look, I'll try not to explain everything, but Tasmania, the east coast, the phenomena of the East Australian current. My first job was actually sitting on a boat going down the east and doing the East Australian Current project with John Church and company. So I actually had a physical oceanography career before meteorology. It comes in jets. It's actually, if you looked at the Humboldt current and other currents, it's a continuous current, whereas the East Australian current is a very peculiar current. It occurs in little jets. So you won't see a continuous stream going down there. So if you like, the average has shown you that the little jets of current that have been pushing that warmer air down there, on average, disappear. But the difference for Tasmania has been that it's accumulated that warmer water, and so you've actually got and probably some of the upwelling that might normally occur has failed, and so you've got an accumulated temperature increase that's actually, on average, warmer than it should be. Yeah.
David Egan.
Yeah, thank you. Thank you, John. Enjoyed your presentation very much. Many of us here would have experienced the River Murray flood in 1956. I was about 7 at the time. I was in the southeast, and there's water everywhere, and draining and that. But I often wonder now, over our last 12 months and the rain we've had, how does that compare to 1955, 1956, and is it much of the same thing happening?
Yeah, look, the 56-57 is a multi-year La Nina event, and so what the fascinating thing about our climate, we have one of the most interesting climates in the world. In a world that's warming, we have to understand the variability of our climate. So on one hand, in the debates that we see out in the world, in our community, our variability is important to understand, and the context of the background global warming. The 56-57 is much more akin to the 10-11-12 event. It just didn't drag that moisture right down into us. It stayed up around Brizzy and down the east coast. It's just a trick of nature that it didn't quite make it to us in terms of that event. But the Murray was certainly being loaded up in that event. It's really interesting in that the 10-11-12, we've actually got more water in the Murray out of this particular event right now because of the strength of that Indian Ocean push. So, and I will say, we're still discovering the science of how this all works and the predictability of it. So it's actually still quite an area in which we're doing a lot of research. Yeah.
I think we've probably got time for one more question. Lisa?
it is fascinating to look at what the science are being driven to demonstrate, because we keep getting asked these questions. Climate change attribution has become a major area of research within universities in the last 2 to 3 years, because people wanted, when we get a weather event, the natural comment is, well, one weather event doesn't make a climate. And it's actually now being discussed about a weather event, how much of it was climate change. So that's coming through now. And in some respects, I would bow to my climate research colleagues and let them answer the question. But rather than fill you up with, what I think, because I think it's there in the literature, and and look, one of the things I would recommend, you've all got mobile phones and smartphones now. There's a wonderful app that you can look at where you can actually, quite readable app, in terms of those exact sorts of questions that you've just asked, okay? And it's called Skeptical Science, the app. If you load it down and you ask that question, it's got exactly that question answered. So I'd recommend to you to actually get Skeptical Science. And what it does, it links to all of the papers that are being used, that are currently being updated all the time, that answer those sorts of questions. I really recommend that.
Thank you very much, John. Look, it's a great presentation from you today, and I'm sure you've illuminated quite a few of the members here with some of the impacts on how global warming is affecting us. So, as a token of our appreciation, thank you very much for speaking today, and I'll now call Adrian and Sister Nino to close the meeting. Thank you.